I'm going to jump right in because I know we have limited time. So I'm going to just quickly define. First, I need to acknowledge my co-authors, Swati Nadav, who are currently working on the project, Steve Choliak, Francesco LaRocca, who are among many of people who are getting taken from academia into high-tech industry. Steve's at Google, Francesco's at Apple, Derek Nankivell, and Marty Banks here at Berkeley. Okay, longitudinal chromatic aberration is an axial shift in the image as a function of wavelength, and it's caused by dispersion of the ocular media. As a result, if green light is focused on the retina, blue light focuses in front or is myopic, and red light is focused behind or is hyperopic. Transverse chromatic aberration is a lateral shift in the image as a function of wavelength. And as illustrated here, transverse chromatic aberration can arise from a pupil displacement relative to the optical axis, like is what's shown here, or with oblique incidence of the light through the optics. Chromostereopsis is a phenomena whereby the apparent depth of an object depends on the wavelength. And the cartoon on the right shows a very compelling example. I hope it's playing. It's playing kind of slowly for me here. There we go. And this is widely believed to arise from transverse chromatic aberration in the eye, although other factors like Stiles-Crawford effect are also considered to play a role. And the illustration here shows how it works. Light from an actual object at some fixed distance, polychromatic light will pass through the eye and will get laterally displaced because of transverse chromatic aberration. In this particular example, the blue light is displaced nasally, which is the most common direction that transverse aberration occurs in the eye. So as a result, there's a disparity between the red and the blue images landing on the retina. And if you trace the rays back from the locations where they strike the retina, you can see it's quite clear that blue light then will appear to originate from objects from locations further than the actual object, and red light will appear to originate from locations nearer, giving rise to a sense of depth. So there's been a tremendous amount of excellent work by many people to study chromatic aberration. In the last few decades, people like Melanie Campbell, Larry Tybus, Arthur Bradley, Susanna Marcos, Pablo Artel, to name a few. And so we know a lot about chromatic aberration. Longitudinal chromatic aberration is similar in all humans. Atchison and Smith have a very nice study summarizing that. Although if you look at individual data, the variability is still quite high. And these are some examples of papers that you can look at to see what the variability is. TCA is small at the fovea or along the line of sight. It's variable between individuals, and there's a slight tendency for shorter wavelengths to be displaced nasally on the retina relative to red light. As I had shown on the previous slide, the magnitude of chromostereopsis is generally predictable by the chromatic disparities caused by the perceived TA. And the results of correcting LCA for fine foveal vision are mixed. Some show dramatic improvements, some show less so, depending on the task. But there's still a lot we don't know, and here's a short list of things we don't know about chromatic aberration. And given the time constraints, I'm just going to focus on a few: how TCA changes with and without LCA correction, what the benefits of combined LCA and or TCA correction are for visual acuity, and then the relationship between TCA and chromostereopsis with larger pupils after LCA correction. And to tackle the questions, we've designed a novel system to test. It's called BVAMS, the Binocular Varichrome Accommodation Measurement System. This is a photograph of the system as is in the lab. Here's a schematic, which is a little easier to interpret. The BVAMS has independent channels for both the left and the right eye. Each eye has its own high-resolution OLED display, pixels of 10.23 arc minutes in the way they're configured here in the system. And there are subsystems for adjusting the focus here with focus tunable lenses. There are subsystems for changing the binocular convergence and subsystems for adjusting and tailoring an LCA correction uniquely for each eye. And I'm going to go through these in order. So just looking at one eye here, there's a focus tunable lens. It's an opto-tune lens that we can adjust to correct for the refraction of the individual and adjust the virtual display distance that the subject would see. There's a binocular vergence correction using a tip tilt mirror conjugate to the pupil plane here that can change the apparent direction of the display in the left eye only. So we can, as we adjust the distance of the object, we can also adjust make it compatible with make a binocular vergence compatible with the viewing distance, or not. We can adjust them independently. And then finally, we have a unit here. We call it a trombone, but it allows for variable longitudinal chromatic aberration correction in each eye. And this is the principle of what we call a varichrome correction. First of all, there's an achromatizing lens that for unity magnification has a chromatic aberration that is equal and opposite to that of a typical human eye. However, the magnitude of the chromatic aberration correction can be adjusted by changing the magnification of the beam, or how much of the ACL is used in the system. And I'm showing three configurations where the beam is small and the beam is larger. The larger diameter beam imparts more chromatic wavefront offsets at the edges of the beam. When you impart more chromatic offsets and you demagnify the beam back down to a fixed pupil size at the exit pupil here, which is the same in all configurations, that amounts to a greater correction of the LCA. So the complication of implementing this, though, is that we need to maintain an afocal system, and we need to keep the exit pupil with a fixed size and at a fixed axial position relative to the final lens of the system. And so we design this with a pair of focus tunable lenses, two opto-tune lenses on either side of the achromatizing lens, and then integrate them into a trombone in the system as I had shown on the previous slide. So now let me talk about experimental procedures that we use to measure the various properties of chromatic aberration. First of all, if we want to measure longitudinal chromatic aberration, we use the classic method. Just simply adjust the opto-tune lens in front of the display to achieve best focus for red, green, and blue primaries of the display independently. They're very narrow primaries, so we can compute the difference in refraction between them to compute the LCA. For TCA, we use a version of a vernier alignment task whereby the subject is asked to adjust the blue disc to generate an apparent alignment between the blue disc and the red annulus. And after a correction, the image on the display might look like the right, and that's because on the display the blue and the red targets have to be offset to compensate for the individual's transverse chromatic aberration. And finally, a chromostereopsis measurement involves having the subject look at a blue and a red target, decide which one looks closer and which one looks further, and then the experimenter adjusts the offsets, the disparity between the red and the blue targets in the right and left eyes to find the position where the two bars are perceived to be in the same depth plane. Finally, visual acuity measurement. We use a tumbling E task for the staircase procedure, psychometric function fit, and we're measuring visual acuity under three viewing conditions. One is essentially monochromatic, just using the bleed green primary. One is polychromatic with black letters on a white background. And then finally, polychromatic, though, with a TCA correction. And I want to point out that in our system, we correct the TCA digitally by rendering images with lateral offsets between the blue, red, and green primaries of the display. These offsets are rendered with subpixel resolution, 10 times subpixel resolution, and with anti-aliasing. And then for each of these viewing conditions, we can measure visual acuity with LCA present uh, and or corrected, and TCA present and or corrected, giving rise to 4 configurations there. So let me show you some preliminary results. These are experiments that are underway. And I'm going to show you preliminary results, summarize them, but be careful about taking any conclusions from this because we only have a handful of subjects. And really the conclusions should be drawn only after many subjects have been tested. But LCA, this is pretty straightforward. The chromatic aberration of the individuals that we tested so far show typical trends, typical amounts of variability, and they fall along a curve given by the Cauchy equation shown in Atchison et al. And so it follows expected variations. Transverse chromatic aberration, and I apologize for not showing a plot, but there are a lot of parameters, and so I found it easier to show in the form of a chart. But let me show that the LCA corrected condition, when the LCA is corrected with the trombone system, the TCAs, the perceived TCA that we measure, are generally greater in the LCA corrected condition. This is reminiscent of an increased TCA found after correcting monochromatic aberrations in a study led by Susanna Marcos, published just last year. So TCA is not necessarily constant. It depends on the quality and properties of the image that lands on the retina. Also, just want to point out the signs here now. The sign of the TCA in the X direction in the right eye, a negative sign means the blue light is displaced nasally on the retina compared to red. Whereas a positive sign in the left eye means that blue light is displaced nasally on the retina in that eye. Collectively, a displacement in the left and the right eye, lateral displacement in the left and the right eye is what gives rise to the binocular disparity. And so we calculate the difference between these, and they're computed here. And a positive sign of this value means that a blue target should appear further than red in the chromostereopsis experiment, as I had described earlier. So with the binocular disparities that we calculate, we compared those to the binocular disparities that we had to do in the chromostereopsis experiment to eliminate the chromostereopsis. So the y-axis shows the results of the chromostereopsis experiment. It indicates the disparities on the axis here that are required to eliminate it. And we're comparing that against the binocular disparity computed from the TCA, as I had shown on the previous slide. And as you can see, and the gray line is or the dashed line is a 1-to-1 line. And as you can see, especially in the LCA corrected condition, these fall on the 1-to-1 line. In other words, the chromostereopsis under LCA corrected conditions are well explained by the computed disparity from the transverse chromatic aberration measurements. Also for the LCA present condition, although it's a little less clear, there are blurs in the LCA corrected condition, or LCA present condition, I'm sorry, that may add other factors that give rise to subjective impressions of depth. So finally, I want to show our early visual acuity results. And bear with me, there are a lot of conditions to walk through, so I'm going to take you through it step by step. There are 2 subjects. Within each subject, we have an LCA present condition and an LCA corrected condition. And for each condition, we're testing visual acuity under 3 different viewing, different types of letters. And so in the first case, I want to show that the visual acuity is quite good. We're doing better than 20/20 for the 2 subjects shown here. And if we test vision with monochromatic light under an LCA present or LCA corrected condition, we ought to see no difference. And in fact, that's the case. This is in effect a control condition. With white light, the visual acuity is barely but moderately worse in the LCA present condition, as expected because of blur from chromatic aberration. This is with the transverse chromatic aberration present. When we correct for the transverse chromatic aberration in the LCA present condition, as expected, we see really no measurable change because the main source of blur is the longitudinal chromatic aberration itself. When we correct for the longitudinal chromatic aberration in white light, but not the transverse chromatic aberration, the VA visual acuity is moderately worse than in the monochromatic condition. And then finally, when we correct for the LCA and the TCA, the acuity gets better and approaches the monochromatic condition. And just want to point out that the TCA in subject 1 was higher than it was in subject 2, and that was the subject who benefited more from the combined LCA and TCA correction. So, but like I said, be careful about taking these as conclusions because we have a handful of subjects. But nevertheless, the trends, expected trends are beginning to emerge in these data. So let me summarize where we're at. So BVAMS is a flexible system for testing the effect of chromatic aberration on vision, and happy to report that it elicits excellent visual performance. The transverse chromatic aberration we find depends quite dramatically on whether or not we correct the LCA prior to the measurement. TCA, as others have shown, is the primary factor giving rise to the perceptive chromostereopsis. And in the visual acuity measurements, the expected trends are emerging, but more data needs to be collected before any strong conclusions can be drawn. But I just want to point out one thing, that simply correcting the LCA might not be enough if that's what you're interested in doing, because it may actually increase the deleterious effects of transverse chromatic aberration on fine visual tasks. So thank you for your attention. Happy to take any questions now or in the panel discussion. And if anybody's interested in working as a postdoc or a research assistant on projects like this, please drop me an email. Thank you.